Here we're asked to solve for x, y and z. We've got a system of homogeneous equations. It's equal to 0. So we've got homogeneous equations here we're asked to solve. It would be interesting to first of all find the determinant where we can make up the matrix. So matrix A would be equal to 1, negative 1, 1, 2, negative 1, 3, and 5, negative 4, 6. So the determinant of A, if we could go plus, minus, plus, so that'll be 1, determinant of negative 1, 3, negative 4, 6, minus will be plus 1, 2, 3, 5, 6, and then plus 1 again, 2, negative 1, 5, negative 4, and that'll be equal to negative 6 minus negative 12, so that'll be 6. And then this will be 2 6 are 12 minus 15, which will be negative 3. And this one here will be 1 outside of negative 8 minus negative 5, so that'll be minus 3. And so the determinant of this matrix will be equal to 0. So it's got a determinant of 0. Now, we've said in the previous lecture the theory is that if the determinant of this matrix is equal to 0, therefore that implies that we're going to get multiple solutions for x, y, z. Okay, so let's just see. So we've got our, we might just write this down again. So we've got x minus y plus z equals 0, 2x minus y plus 3z equals 0, and 5x minus 4y plus 6z equals 0. One way to do these is to make all those terms equal to 0 by combining 1, 2 and 3. We leave 1 alone. So we've got x minus y plus z equals 0. Now if we multiply this top line, row 1, by 2 and take it away from row 2. So we've got 2 minus 2 row 2 of 1. So multiply that by 2 and take it away from there, we get 0. Negative y, take away negative 2y, will end up with plus y. And 3z minus that will be just plus z equals 0. So that's good. And then we've got to get rid of this 5x, so we'll take 5 times 1 and take that away from 3. So it'll be that minus 5 times that will be 0. That minus 5 times that. Now minus 5 times negative y will be minus negative 5y, so that'll be plus 5y. So I get plus y. And then I get this minus 5 times that will be just z equals 0. So this will be 2a and this will be 3a. So this looks like we've got a little bit of a stalemate going on here. We want to get rid of that y, that is the next step, so we can go leave 1 and 2 as they are, 1 and 2a, so we've got x minus y plus z equals 0, that's equation 1 we haven't touched. This one is from the line above and we get y plus z equals 0. and that's 2a. Now we want to get rid of that y there, so it'll be 3a minus 2a. So we're going to take that from that, and we get 0. Z from z is 0 equals 0. And so that'll be 3b. Okay, so where does that leave us? We said we're expecting to get multiple solutions. So from here, we can get y, so using that one there, we can get y, just take the z the other side, is equal to negative z. So we've got a value of z, y is equal to negative z, and then we've got x, substituting in the top one, y is equal to, so you've got x minus, now y is equal to negative z, plus z is equal to 0. So therefore we can say that that's minus minus be plus, so you've got x plus 2z equals 0, so x is equal to negative 2z. So if we were to write this as a solution set, we've got x is equal to negative 2z, and we've got y is equal to negative z, and z can have a value. So what that means is that if you said, like, okay, if z is equal to 10, then y would be equal to negative 10, and x would be equal to negative 20. So negative 20, negative 10, and 10 would be a set of solutions, a set of values for x, y, and z that would satisfy our original equation. How many solutions are there? There are an infinite number of solutions. This just gives the pattern that whatever value you pick for z, then y is going to be the negative of that, and then the x will be negative 2 times that value that you chose for z. So that backs up the theory that if the determinant of this matrix is equal to 0, then you're going to get multiple solutions in x, y, and z. Okay.